Toshiba device and storage. CMOS logic ICs. E-learning. 3. Basic CMOS logic ICs. Operations of typical ICs. Basic CMOS logic ICs. CMOS logic ICs are broadly divided into combinational and sequential logic. This section describes major logic circuits. Combinational logic. Type of logic circuits whose output is a pure function of the present input only. Includes inverters, buffers, bidirectional bus buffers and more. Sequential logic. Type of logic circuits whose output depends on the sequence of previous input values and is controlled by the present inputs. Includes flip-flops, latches, counters and more. Combinational logic, inverters and buffers. Inverters. An inverter is a logic gate whose output, X, is the inverse of its input, A. Buffers. A buffers increase the drive capability to increase the number of connectable signal lines, and perform waveform shaping. A buffer does not perform logical operations. Combinational logic, bidirectional bus buffers. Bidirectional bus buffers, transceivers. There is a type of buffer called the bidirectional bus buffer, transceiver, that can both transmit and receive data with a single input-output terminal. Transceivers can switch the direction of passing signals with the control signal, DIR, so they are used for bus lines that pass data in both directions. A usage example is shown below. When using bus signals bidirectionally, connect both the bus input and bus output to VCC or ground via a pull-up resistor to prevent the input signal from becoming open, undefined, when the signal is switched by the control signal, DIR. Please be careful not to short-circuit the output with the output of the bus line when switching signals. The direction of the A and B pins can be changed easily by changing the value of DIR while G bar is high. Although the directions of the A and B pins can be changed easily, care should be exercised as to the periods during which data are valid. Combinational logic, Schmidt trigger devices. A Schmidt trigger device has a hysteresis band between two input threshold voltages. The following shows the input and output waveforms of a Schmidt inverter with an input threshold hysteresis. In the case of an IC with hysteresis, the positive going threshold voltage, Vp, differs from the negative going threshold voltage, Vn. For a slowly rising or falling input, an input threshold hysteresis, Vh, helps stabilize the output. Even in the presence of input noise or power supply or ground bounce due to noise, an IC does not produce a false output unless the noise or bounce exceeds the hysteresis width. Combinational logic, decoders. A decoder converts binary information from the n-coded inputs to a maximum of 2 to the power of n unique outputs. It is commonly used to increase the number of ports and generate chip select signals. Operation of a decoder. The following shows a logic symbol, truth table, and timing diagram of a 3 to 8 decoder, i.e., a decoder with 3 inputs and 8 outputs. The following shows how a 3 to 8 decoder is used to generate 8 chip select signals from 3 inputs, A, B and C. When A, B, and C are all low, only the Y0 bar output provides a logic low, causing IC0 to be selected. This figure indicates that, with a combination of 3 inputs, an arbitrary chip can be selected from up to 8 chips. Combinational logic, multiplexers. A multiplexer selects one signal from multiple input signals and forwards it to a single output line. The following timing diagram shows how one signal is selected from 2 inputs. When the select pin is low, 0, a signal is forwarded from the A pin to the Y pin. When the select pin is high, 1, a signal is forwarded from the B pin to the Y pin. Logic schematic of a 2 to 1 multiplexer is shown below using 74VHC157 as an example. Logic schematic of a 4 to 1 multiplexer is shown below using 74VHC153 as an example. Combinational logic, analog multiplexer demultiplexers. An analog multiplexer incorporates analog switches to select one signal from multiple analog inputs and forward it to a single output line. The analog multiplexer can also be used as a demultiplexer since analog switches can transfer a signal bidirectionally. Combinational logic, analog switches. An analog switch can conduct an analog signal such as a sine wave signal in either direction. It passes a signal when on and blocks it when off. An analog switch is composed of a pair of N-channel and P-channel MOSFETs connected in parallel in order to reduce on resistance and improve the linearity of I/O characteristics. The datasheet for the analog switch shows typical sine wave distortion, maximum frequency response, feed-through attenuation, crosstalk, and other specifications as analog switch characteristics. The following shows the logic symbol, truth table, timing diagram, and logic schematic of an analog switch. Sequential logic, latches. A latch can retain data under specific conditions. There are several types of latches such as D-type and RS, reset and set, latches. As an example, the following describes the operation of a D-type latch. For example, a D-type latch has an input data pin, D, a latch enable pin, LE, and an output data pin, Q. In this case, when LE is low, Q retains the previous value of D. When LE is high, Q follows the changes of D. The following shows the timing diagram of a D-type latch. Sequential logic, flip-flops. A flip-flop can retain data under specific conditions. The word flip-flop is sometimes abbreviated as FF. There are several types of flip-flops such as D-type and JK flip-flops. As an example, the following describes the operation of a D-type flip-flop. A D-type flip-flop differs from a D-type latch in that the D-type flip-flop retains output data even after the clock is set inactive. For example, a D-type flip-flop has an input data pin, D, a clock pin, CK, and an output data pin, Q. This flip-flop latches input data, D, on the rising edge of CK and transfers them to Q. Q remains unchanged till the next rising edge of CK regardless of the input data, D. In other words, Q retains the input data, D, latched on the previous rising edge of CK. The following shows the timing diagram of a D-type flip-flop. Some flip-flops have a clear, CLR, or preset, PR, input pin that is used to initialize the internal state to a known value. Operation of a D-type flip-flop. The following describes the operation of a D-type flip-flop using a logic schematic. A D-type flip-flop consists of two D-type latches. When a rising clock edge is applied to CK, D-type latch 1 is activated. While the clock, CK, is high, D-type latch 1 remains active, and thus the first clocked inverter in D-type latch 2 is also active. Therefore, the data held in D-type latch 1 are transferred to the output, Q, as highlighted by the blue arrow. The output remains unchanged even if the input changes state. When a falling clock edge is applied to CK, D-type latch 2 is activated. As a result, the data held in D-type latch 2 continue to appear at the output, Q, as highlighted by the green arrow. Again, the output remains unchanged even if the input changes state. It should be noted that the value of the output, Q, is unknown until a known input is latched on the rising edge of the clock, CK. Sequential logic, counters. Counters count up or down sequentially on every clock, CK, pulse. A 4-bit counter can have a modulus of up to 16, an 8-bit counter up to 256, and a 14-bit counter up to 16,384. Some counters have the CLR input that is used to initialize the internal state to a known value. Counters are incorporated in digital timers, electronic calculators, stopwatches, and many other devices. Counters are broadly divided into asynchronous, ripple carry, and synchronous, parallel carry, counters. Let the propagation delay time of a single flip-flop be TPD. Then, an n-stage asynchronous counter incurs a large delay equal to n times TPD. It should also be noted that the asynchronous counter could produce hazards when the counter output is fed to a logic gate. Logic schematic of the 74VHC1614 4-bit counter. Synchronous, parallel carry counter. Timing diagram. The following shows the timing diagram of a typical synchronous, parallel carry, counter, which counts upward sequentially on each edge of the clock, CK. Sequential logic, shift registers. Shift registers can be configured for serial parallel, SI, PIA, or parallel serial, PI/SO, conversion. Parallel serial conversion helps reduce the number of transmission lines, i.e., transmission bit width. Some shift registers have the CLR input that is used to initialize the internal state to a known value. The following shows the logic symbol and truth table of a shift register. A shift register is composed of multiple flip-flops. Operation of a shift register. The following describes the operation of a shift register using a logic schematic in a timing diagram. A shift register is composed of a cascade of flip-flops in which the output, Q, of each flip-flop is connected to the data, D, input of the next flip-flop in the chain. A serial input, SI, is applied to the data, D, input of the first flip-flop. The data from SI are latched on the rising edge of the clock, CK, and appear at QA. With 4 clock pulses, the data from SI are transferred to the fourth flip-flop. As a result, the serial input, SI, is converted to parallel output data appearing at QD, QC, QB, and QA. Types of shift registers. Logic schematic of the 74VHC1648-bit SI, PO shift register. Logic schematic of the 74VHC1X58-bit PI, SO shift register. There are serial in, parallel out and parallel in, serial out shift registers.